We're going to explain diagnosing NaN, not a number, loss during TensorFlow training. NaN loss is a frustrating problem that abruptly halts your training process. It indicates that your model has encountered an invalid numerical result, rendering the loss calculation meaningless. Let's explore common causes and debugging strategies. 1. Data issues. This is often the culprit. Examine your training data meticulously. Are there any NaN or N-for infinity values present? These can propagate through your computations, leading to NaN loss. Use TensorFlow's tf-debugging.checkNumerics function to detect them during training. If you find them, investigate their source, perhaps a flawed data preprocessing step or corrupted data file. Cleaning or removing affected data points might resolve the issue. Consider adding input validation checks to your data pipeline to prevent such values from entering your model in the first place. 2. Learning rate problems. An excessively high learning rate can cause your model's weights to oscillate wildly, potentially leading to numerical instability and NaN loss. Try reducing your learning rate significantly, perhaps by an order of magnitude, e.g., from 0.1 to 0.01. Experiment with different optimizers. Some are more robust to unstable gradients. Learning rate schedulers, which dynamically adjust the learning rate during training, can also help prevent this. 3. Activation function issues. Certain activation functions, like the sigmoid or tanh functions, can saturate when inputs become very large or very small. This saturation can lead to vanishing gradients, slowing down training and potentially resulting in NaN loss. If you're using these, consider switching to ReLU or its variants, leaky ReLU, ELU, which are less prone to this problem. Ensure your activations are within reasonable bounds. Clipping values to prevent extreme values can be a preventative measure. 4. Gradient explosions. Very large gradients can also cause numerical overflow, resulting in NaN loss. Gradient clipping, which limits the magnitude of gradients, is a common solution. TensorFlow provides functions for gradient clipping, usually within the optimizer configuration. 5. Model architecture issues. Complex architectures with many layers or intricate connections can be more susceptible to instability. Carefully review your model architecture. Simpler models are often easier to debug and less prone to NaN issues. 6. Numerical instability in custom layers or functions. If you're using custom layers or functions, ensure they are numerically stable. Avoid operations that can easily lead to overflow or underflow. Check for potential division by zero errors. Thorough testing of custom components before integration into your main model is essential. 7. Debugging tools. TensorFlow offers powerful debugging tools. Use the tf-debugging.enableCheckNumerics context manager to catch numerical issues during training. TensorBoard can also help visualize metrics and gradients, allowing you to identify potential problems. Carefully examine your loss function's behavior, as well as the gradients of your model's weights, to pinpoint the source of the NaN loss. Print intermediate values during your training loop to trace the source of the NaN. Systematic debugging, including printing values at different points in your training and using breakpoint debugging in your IDE, is essential for pinpointing the source. Remember to use these tools and techniques in a combination to efficiently debug your model.